Good morning, everybody. My name is Marek Michalewicz. I'm the director of Interdisciplinary Center for Mathematical and Computational Modeling at the University of Warsaw in Poland. And I have a great pleasure of starting this new initiative, very freshly conceived just a week ago. Or to run a series of ICM seminars in computer and computational science. And we have ambition to run it weekly and worldwide, and the event is supposed to be free. And one of the reasons of starting this seminar series is that we just last week ran a 3-day conference in a series of conferences that was the 6th edition of Supercomputing Frontiers Europe, which turned out to be a quite successful event. Normally, of course, we run it as a stationary event. We run it for 3 times in Singapore and 2 editions in Warsaw, Poland, and the 3rd edition was very different. About 2 weeks before opening of the conference, we could see how serious the situation with pandemic is. So we made a decision to convert it into a virtual event, and it turned out that the virtual event brought us much more participants than we could have ever imagined. And this is very much in the spirit of open science. And ICM for years has been in forefront of promoting, supporting, and creating open science access in Poland. We are responsible for negotiating and obtaining licenses from all major publishers to all scientific literature for all of the Poland. So we make sure that about 600 scientific institutions in Poland have free access to something of the order of 8,000 scientific journals, title journals. We also have a quite large group at ICM of people who are responsible for providing open access to Polish scientific journals and cultural journals. And right now we have over 1,000 titles of journals in open access. And in the similar spirit, I thought that creating a series of seminars that will be completely open and reasonably easy, accessible to anybody with interest in the topic might make sense. And I was incredibly lucky and honored to receive acceptance for my invitation from Professor Scott Aaronson from University of Texas. And of course, lots of people know about Professor Aaronson's work, and I hope that most of you are already quite familiar with one of his creations, which is this very special book. And if you don't, please spend your time reading it. It's not only extremely enlightening, it's a pleasure to read, but it's also something that opens up your mind, widens your horizons, and goes into so many directions of really fundamental, very deep thinking, not only about quantum computing, but about computing in general. So we are very fortunate to have Professor Aaronson, who not only writes beautifully, but also can convey his ideas in a brilliant way. So with this, I would like to welcome Professor Aaronson to give our first seminar in computer and computational science. Thank you very much.
Can people see me? Or
hello? Yes, we can hear you,
right.
but not see you
yet. Hello?
We can hear you, but we cannot see you yet.
You can't see me. Okay. Well,
please try to enable the camera.
Yeah. Okay. Good. Can you see? You can see me now.
Yes, we can see you.
All right. Great. Okay. And now, so let me enable the screen sharing then. Okay. Second. Okay. Good. Can you see my slides now?
Okay. Yes, we can see them.
Sorry, can you see my slides?
Yes, they're fine.
Okay, great. All right. Well, thank you so much for inviting me and for the introduction. This is actually the first talk that I've given on this lockdown, first virtual talk, so I'm honored to do it. And so what I want to talk about is quantum computational supremacy and its applications. Now, when I did a Google image search for quantum computer, what you see there is one of the first things that came up. Now, I'm a theorist. I'm not an engineer, so I'm not actually building quantum computers, but I've visited enough quantum computing labs to be able to tell you that that's not exactly what they look like. Maybe it reminds us that we're sort of harnessing nature to do computation in a new way. And as everyone knows, the goal with quantum computing is to do things that just could not be feasibly done with even the largest supercomputers that exist on Earth, or that could plausibly exist. It is amazing that we can do such things. The things that we can do are rather special in nature that we hope to do. But can we do even those things? And so that's very much the question that I want to talk about sort of getting the first evidence that quantum computers can outperform classical computers for anything. Okay, well, I know that we have a sort of a diverse audience and people with lots of backgrounds and interests. So why don't I start by just trying to summarize quantum computing on one slide. Now, that's hard to do, but I can I'm not a physicist. I'm a theoretical computer scientist. And so I am sort of allowed to let you in on a secret, which is that quantum mechanics is actually much simpler than a lot of people think it is once you take the physics out of it. We can start with just a certain picture of a classical computer, that it has some memory. So its internal state we can think of as just a string of n bits, let's suppose, with no loss of generality. We then do logical operations on those bits, like we set one bit equal to the XOR of two specified other bits, and so on. And I also want to consider a probabilistic computer, so one that could set a bit to be a 0 or 1 with equal probabilities. You could imagine that every time that happens, it could cause a branching of the computer's state. So we could say, if we don't know what was the outcome of the coin toss, then really the configuration of the computer is given by a probability distribution. Right now, a probability distribution over n-bit strings is already an exponentially large object. It's a vector of 2 to the n real numbers. right? One for every possible string. But we haven't yet said anything about quantum mechanics, right? And in practice, the way that we might get truly random numbers is, using quantum mechanical processes. But if a computer is only using quantum mechanics in that limited way, then we would not call it a quantum computer. We would just say that it is a classical computer that uses randomness, and so we can do computations that way. You can imagine that every step in the computation is actually corresponds to some linear transformation of that vector of 2 to the n probabilities, representing all the possible strings. Now, of course, when we look at the computer at the end of the computation, we don't see the entire vector of probabilities. All we see is a single string. Each bit is either 0 or 1. And if we want to know how likely it is to see a given string, well, we calculate its probability. One way to calculate the probability of a given string would simply be to sum over every possible path through all the states of the computer that could have terminated at that string, right? So each path contributes some probability to the total. And for each path, the probability of that path is simply the product of all of the probabilities of all of the choices that are made along that path. Okay, so I've simply been pedantic about describing a classical computer with randomness, because if you understood what I just said, then a quantum computer is a very, very simple change to that. A quantum computer is what results if we were to say, let's sort of incorporate one of the central insights of physics, really, of all time, but certainly of the physics of the early 20th century. And this is that the different possible configurations that a system could have do not just have probabilities. They have to be assigned a different kind of number, which is called an amplitude. Now, amplitudes can be positive or negative, and they can even be complex numbers. And the central thing that quantum mechanics says about our world, has said about it since 1926. The theory has not changed in more than 90 years. Is that the state of any sort of, let's say, isolated physical system can be described by a vector of these complex numbers, these amplitudes, one for every possible state that you could see the system in on looking at it. And if we have many different possible configurations, all of them with non-zero amplitudes, then we would also call that a superposition state. Okay, and now you may have heard of a qubit, a quantum bit. That's sort of famously the central building block of a quantum computer. A qubit is just a bit that can be in a superposition of the 0 and the 1 states. So it has some amplitude for being 0 and some other amplitude for being 1. Right? And now sort of the crucial thing is that if I have, let's say, 1,000 qubits, then quantum mechanics is unequivocal that I don't just need amplitudes for each qubit separately. Rather, I really need like 2 to the 1,000 power amplitudes. Okay, I need 1 amplitude for every possible setting of all 1,000 of the bits. And you may notice that 2 to the 1,000 is already more than the number of subatomic particles in the observable universe, for example. Okay, so this is really a staggering claim about nature, that to keep track of the states of, for example, 1,000 measly particles that could each store a 0 or a 1, for example, in their spin states. If those particles can interact with each other, if they can form what we call an entangled state, then nature, to keep track of what they're doing, has to write down somehow more parameters than you could fit in the observable universe. Now, once again, when you look at the bits, you don't see the entire vector of amplitudes. You only see one outcome. And in this case, the probability that you see a given outcome is given by only a slightly different rule than the one that I said before. And this is the famous Born rule of quantum mechanics. And what it says is that the probability that you will see a given output string is equal to the squared absolute value of its amplitude. Okay, so the squared absolute value of a complex number, gives you a real number, a non-negative real number. And to find the amplitude of a given string, in turn, we can just sum over all of the possible paths through the computation that could have terminated at that string, where the amplitude along each path will just be the product of the amplitudes of sort of all of the transitions that were made to stay on that path. Okay, so in short, quantum computing is a lot like classical probabilistic computing, except with vectors. Now, instead of vectors of probabilities, we use vectors of complex numbers. These are unit vectors. Okay, in order to get a probability distribution at the end, we impose that the vector of amplitudes is a unit vector. Okay, so it's a unit vector in the 2 norm. Okay, but now the real revolutionary thing, of course, is that we denote quantum states using this funny notation, these asymmetrical brackets, which are called the Dirac-Ket notation. Okay, this is simply a notation for the 0, 0, 1, 0, and so forth. These are different different basis vectors in a 2 to the n dimensional vector space. Okay, so now what is the idea of a quantum computer? Well, the central phenomenon of quantum mechanics that makes it different from conventional probability is what's called interference. And what interference means is, if I look at a given possible output state, some of the amplitudes that lead to that, some of the paths that lead to that state could have positive amplitudes, and others could have negative amplitudes. And if that happens, then when I add them all up, the amplitudes will, as we say, interfere destructively and cancel each other out. Okay, and if the interference is perfect, it could even happen that the total amplitude will be 0, meaning that that event will now never happen at all. Right? There were many ways that it could have happened, but the different ways, if their amplitudes point in different directions, they will cancel each other out. Okay, this is what happens, for example, in the double slit experiment, which is sort of the canonical experiment to illustrate the quantum mechanical nature of the world. That's where you fire photons at a screen with 2 slits in it. And you find that if you look at where they land on a second screen, there are certain spots where you never see them appear because of interference. And yet, if I closed one of the slits, then the photons could appear at that place. Okay, so by decreasing the number of ways for a photon to arrive somewhere, I can increase the chance that it gets there. Okay, and the quantum mechanical explanation for that is just that, well, the photon was in a superposition of states. It had some amplitude to go through the first slit, and it had some amplitude to go through the second slit. And if you set things up right, then those 2 amplitudes can sometimes cancel each other out. Okay, so so in some sense, this is the more fundamental sort of operating system that we need to describe the physical world. It's not using probabilities, but it's using these complex numbers that sort of behave as square roots of probabilities. Okay, now a quantum computer you can think of as sort of a lot like the double slit experiment, but on a much more massive scale. Okay, so now we're not talking about a superposition over 2 slits or 2 states, but over 2 to the 1,000 power states, or 2 to the million power. Okay, and all of these are being maintained in superposition, as we do our computation. And now the goal in every quantum algorithm is to choreograph things in a very, very special way, so that for each possible wrong answer, each answer that you don't want, some of the amplitudes leading to that answer, let's say, have positive amplitudes, others have negative amplitudes, so they interfere destructively. They cancel each other out. Whereas the amplitudes leading to the right answer, you would like those to reinforce each other. Okay? If you can arrange that, then when you look at the computer, you will see the right answer with a high probability. If you don't see it, you can always just keep repeating the computation many times from the beginning until you do. The tricky parts are you have to do this even though you don't know in advance which answer is the right one. If you knew that, there'd be no point to the whole exercise. Also, you have to do it all faster than a classical computer could have found the answer, or again, there's not really any point. Okay, so you may have heard that there are lots and lots of ideas being discussed for how to build a quantum computer. And I would say we do not yet have the quantum computing version of the transistor. That is, we don't yet have the technology that is sort of just clearly going to scale, clearly going to beat everything else. We have a bunch of different technologies that let you build small quantum computers, or scale to maybe a certain extent, but that all have sort of complementary weaknesses. Okay, so there's what's called the trapped ions approach, being pursued by a company called IonQ in Maryland, also by Honeywell in Colorado. This is where we use as our qubits the spin states of atomic nuclei. We can trap the nuclei inside of a magnetic field, and we can move them around using lasers. And if two ions are close to each other, they will sort of interact, which will, affect, which will do the steps of our computation, which you can think of as just norm-preserving linear transformations, we call unitary transformations, on that vector of amplitudes. And then you can measure each ion to see if it's spinning up or spinning down. Okay. Another approach uses neutral atoms, cold atoms. It's the group of Misha Lukin at Harvard is a leader in that. Another approach would use photons, the polarization states of photons as the qubits. That's being pursued by a startup called PsiQuantum in Palo Alto. Yet another approach is called topological quantum computing. It uses, it would use a hypothetical new particle that is called a non-abelian anion. So this would be sort of an excitation in sort of an exotic state of matter. Now Microsoft has placed a huge bet on this topological approach to quantum computing, and they're the leaders in that. Including in sort of I think experimental groups that they're funding in Europe. The huge advantage is if this works at all, there is sort of beautiful mathematics that suggests that it could scale much more easily than any of the other approaches. Unfortunately, no one has yet succeeded in making even one of these non-abelian anions, these new particles that you would need. So you could say that so far that approach is at about 0 qubits, okay, compared to dozens of qubits for the other approaches that I'm talking about. Okay, to make it, I hope it will work. To make it work, all you have to do is create this new state of matter that's never been seen before. Okay, now for the rest of this talk, what I'm going to focus on mostly is the superconducting approach to quantum computing. And that is being pursued by Google, also by IBM, also by startup companies, including Rigetti, Also D-Wave, which was an early startup that had an approach to quantum computing that most of us think doesn't really give you speed ups over classical computers when you scale it. But that was also based on superconducting qubits. Okay, so it's very popular. One reason why is that you can use a lot of conventional chip fabrication technology to do it. And also the qubits are quite enormous by the standards of qubits. So they're not individual atoms or anything like that. They are quantum states of currents that are flowing around little coils that are in this chip. And these coils are, you could see them with a magnifying glass. Okay, so they're that enormous. Now, how, in real life, how do you get anything that enormous to behave quantum mechanically, to sort of stay in a superposition of 0 and 1 states? Because, quantum superpositions are very fragile. Well, you do it by cooling the system, cooling your chip down to nearly absolute zero to cause the coils to superconduct. Okay, and superconductivity is a large-scale quantum phenomenon. That is what it is, and so you put the chip in a dilution refrigerator. That's what I've shown at the near the bottom there. This is, it looks like an upside down wedding cake, and it cools the chip to about 1/100th of a degree above absolute zero, so about 10 millikelvin. Which sounds very cold. It's not as cold as one would like, actually, but that can get the qubits to maintain their quantum superposition state for a few tens of millionths of a second. Okay, a few tens of microseconds, and you can control the qubits using classical electronics that are situated outside of the dilution fridge. So you can program in exactly which qubit should engage in what interaction with which of its neighboring qubits and at which time. So in some sense, that is why we call this thing a computer in the first place. That is why it's programmable. Okay. So I'm gonna tell you about for example, the Google device that had 53 qubits. And there are, with the competing approaches, people are also now doing experiments with fully programmable quantum computers, but only with a few dozen qubits, usually, at most about 50, and usually a few dozen layers of operations before everything falls apart. So you might wonder, it's been about 25 years now that people have been seriously working on experimental quantum computing. So, why don't we have quantum computers with 1 million qubits yet? Why is building these things so damn hard? Well, in some sense, the reason why building quantum computers are so hard was understood from the very beginning, and it's the phenomenon that we call decoherence. Okay, so decoherence basically just means unwanted interaction between the quantum computer and its environment. So I told you before that if you look at a qubit, that's let's say in a superposition of a 0 and a 1, right? Then you see only 0 or 1, right? You never see the superposition. The probability that you see 0 or that you see 1 is given by that famous Born's rule. And then after you look, the qubit collapses to whichever outcome you saw, right? So if it said 0, it is now just in the state 0. If it said 1, it is now just in the state 1. Now, the central problem is that it doesn't have to be you who is looking, or for that matter, any your measuring device, or any conscious being, or anything like that. Any kind of interaction between the qubits and their environment that has the effect of carrying away the information as to whether this qubit is a 0 or a 1, is recording that information into the environment, will have the same effect on the qubit as if it was measured. Okay, namely, it will collapse the qubit and make it just behave like a classical bit again. Okay, so what this means is that if you want to build a quantum computer, you have to keep your qubits incredibly well isolated from everything else in the world. Okay, from the radiation and the air in the room, from the various noise modes, on your microchip, on your device, from everything. Okay, but they also can't be completely isolated, because if they are, then they'll just sit there doing nothing. Okay, so they have to interact with each other, and not only that, but do so in exactly the way that you specify. Okay, so that's staggeringly hard, and as you want to do it with more and more qubits for a longer and longer time, it gets even more staggeringly hard. Okay, it is so hard that there were distinguished scientists in the 90s who said this is never going to work. You will never be able to beat decoherence enough to build a scalable quantum computer. Now, in the view of most quantum computing researchers, the fundamental answer, the thing that fundamentally answered those worries, was a great discovery of the 1990s called the theory of quantum error correction and quantum fault tolerance. And what that said, basically, is that you don't have to get your qubits perfectly isolated from the rest of the world in order to do quantum computation. Okay, you merely have to get them very, very, very well isolated. Okay, so, but if you can just push the rate of interaction with the environment to be sufficiently small, then at some point you become able to take the qubits that you care about, and what we call logical qubits, and encode them in very, very clever ways across the collective states of tens or hundreds or thousands of physical qubits, in such a way that even if a small fraction of those physical qubits are to leak their states to the environment, you can detect that, and you can recover the quantum state that you care about from the remaining qubits, and then you can keep going. Okay, so so you could say the central engineering goal in quantum computing research from the 90s until today has been to achieve this fault tolerance. Okay, to get physical hardware that behaves reliably enough that you can start using these quantum error correcting codes to simulate hardware that is perfectly reliable, or essentially perfectly reliable. Okay, we are not there yet. Okay, the achievement of quantum supremacy that I'm going to tell you about did not use any quantum error correction or quantum fault tolerance at all. Okay, so it just used bare physical qubits. Now, error correction is, the big milestone that everyone is working toward. Okay, and until you've got error correction, we think that you're going to be limited to probably, doing quantum computations with a few hundred qubits at the most. Okay, but now, the reason for the excitement and hype, for about near-term quantum computers, to the extent that it's founded on anything, that it's not just, pure hype. The reason for the excitement is, well, it looks like even without error correction, one should be able to do things with, at least, maybe a couple of hundred qubits, and that could already be enough to outperform any classical computer that is currently on Earth, or that we could plausibly build, at least for some very special applications. Okay, so this brings me to quantum computational supremacy. Okay, so what does this? What is this? So quantum supremacy is a term that was coined by my good friend, the physicist John Preskill, who I'm showing here, in 2012. There's been some controversy about this name. Some people think that it's promising more than we can deliver, or it's promising, that sounds too hyped. Other people think that it reminds us of of very evil kinds of supremacy. But in any way, you know, if you have any problems with this name, you should not blame me. You can blame John Preskill. Okay, so what he meant by the term, and what I'll mean by it also, is the use of a quantum computer to solve some well-defined problem much faster than any available classical computer running any algorithm that we currently know. Okay, so notice that I did not say a useful problem. Okay, so, you know, think of this like the Wright brothers airplane, or like Enrico Fermi's nuclear reaction, right? The purpose is just to prove a point, you know, not to build, you know, in effect, we're saying, you know, forget about solving, you know, problems for customers, right? That might get, you know, or sort of commercially useful problems that might get, you know, the headlines because that's what people want to hear, that you're using a quantum computer to solve your traffic flow problem or your, you know, industrial supply chain problem faster. But you know, there have been many claims of that kind, and in case after case after case, it was never clearly established that you're getting any advantage over a classical computer. Okay, so let's, for the time being, just forget about all of that and just say, can we get a speed up that is clear, you know, regardless of whether the problem is useful or not, right? And this to me seems like an obvious first step, right? Let's establish the reality of quantum speedups. Okay, so maybe a little bit more precisely, what do I mean by that? Well, you know, the problem that we're solving does not need to be useful, but it does need to be something that is mathematically well defined. Okay, so in other words, we need to be able to specify in advance what are the outputs that we're looking for, right? Which outputs are valid, which ones are not valid. We need to be able to tell a competitor using their classical computer, you know, here is, you know, mathematically the function that we want to calculate, or here is the outputs that we want. Now you go and you try to find those outputs in the fastest way that you can. Okay, the problem cannot be something like just simulate my quantum device. Okay, that doesn't count as a problem because you know, that depends on all kinds of messy details of the hardware. Okay, it has to be something more abstracted than that. Okay, so you know, and I stress this because lots of people say, well, we have all kinds of molecules, you know, in nature that we have trouble simulating, even using the biggest supercomputers, you know, for reasons of you know, the sort of the enormity of, you know, the quantum states, of the number of amplitudes. So why can't we count any of those molecules as just quantum computers that solve the problem of simulating themselves? I know I say simulating yourself doesn't count. You know, for something to count as a computer at all, I want it to be at least logically possible for it to output a wrong answer. Okay. And then, you know, there's the problem that, you know, in theoretical computer science, we always really care about scaling advantages. Okay, so what we really want is to solve something in polynomial time with a quantum computer, you know, with polynomial scaling that we think would require exponential scaling for any possible classical algorithm. Right? This is really what we want. But now the problem is when you do an experiment, you just have some fixed number of qubits, like 50 or 100, right? So you never observe polynomial or exponential, right? You observe how many seconds it took you to solve this concrete instance. So what I say is, well, I want a real observed speed up that is to do something in a few seconds or minutes that would require many days or weeks or years with the largest supercomputers that now exist. But, you know, I also want the only explanation that anyone has for this speed up to be in terms of quantum computation. Okay, in terms of, well, the reason we saw this speed up is that you know, the state of this quantum computer was a vector of 10 quadrillion amplitudes or whatever, and you know, if to simulate that with our classical computer, we think that we would need, you know, at least 10 quadrillion steps or something of that kind. Okay, so I want to, you know, I want to be able to rule out, you know, any explanations for the speed up that depend on, you know, more mundane details of the hardware and that are not really about quantum computation. Okay, and not sort of reflective of what we hope will be an actual scaling speed up that would get better and better as we went to larger and larger instances. Okay, so, you know, another way to summarize quantum supremacy is that, you know, for me personally, I feel like, you know, the #1 application of a quantum computer is just to refute the people who said that quantum computing was impossible. So here, you know, I've shown some distinguished computer scientists and physicists, Gil Kawai, Leonid Levin, Oded Goldreich, Robert Liskey, Michel Diakonov, Bob Laughlin, who've all said in various ways that they don't think that you're going to get a, you know, a speed ups over classical computers, that quantum computing is not going to really scale. You know, I would like to sort of be able to do a crucial experiment that says, you know, where these people, you know, then, you know, the ball is in their court to explain it. Okay, and I think that in some sense that is what Google has done just this fall. Okay, so you know, before you know, the entire world was taken over by coronavirus, one of the, you know, the biggest stories, certainly in the science news, was the announcement by Google just in November that they achieved this milestone of quantum supremacy with their superconducting chip at their lab in Santa Barbara. And so here I've shown, you know, some of the news headlines about it. It was actually very funny what happened. The story leaked to the press like a month before their paper was published in Nature. This was because NASA, which had some co-authors of the work, accidentally posted a draft of the paper on its public website. And then before they could take it down, Google alerts actually found it. So, you know, Google actually undermined itself in some sense. And so this story started getting into the press, and, you know, no one knew what to make of it. And meanwhile, Google was under embargo because you know, because of Nature's policies, so they couldn't comment on it. So I sort of, you know, had to become an unofficial spokesperson, and so I started blogging about it. This is my blog that you see here. So okay, so what was Google claiming to do? So they built this chip called Sycamore, which has 53 superconducting qubits. They're arranged into a two-dimensional grid that's roughly rectangular. If you're wondering why 53, well, they built 54 qubits, but one of them didn't work. And then they use this device to output samples from a probability distribution over 53-bit strings. This probability distribution was almost, but not quite, the uniform distribution. Okay, if it was the uniform distribution, well, that's easy to sample yourself. You don't need a quantum computer to, you know, generate perfectly random strings. That would not be interesting. Okay, what is interesting is that these strings, you know, the distribution being sampled had little tiny deviations from uniformity, you know, on the scale of about 0.2%. Okay, some strings were just a little bit more likely to appear than other ones, and you know, in a way that is supposed to reflect the quantum interference going on among these 2 to the 53 power quantum mechanical amplitudes. Okay, so the good news is that the device, you know, there's a lot of noise in the device, as you can see. You know, you're like 99.8% noise and only 0.2% signal. Okay, but the good news is that the machine is fast enough that you can take many samples in order to try to extract a signal from that noise. So you can take, so each sample takes a few tens of microseconds. So in about 3 minutes, you can take about 5 million independent samples from this probability distribution. And you then, using a classical computer and using a lot of computation time, you do statistics on the samples that you saw in order to try to extract a signal corresponding to that quantum interference effect, that, you know, the sum strings being a little bit likelier than other ones. Okay, and then comes the question for the theoretical computer scientists, for me and for my friends, which is that now we have to ask, well, how hard would it be for a classical computer to do that same thing? So, you know, is there a classical algorithm that could even just generate samples that would have the same kind of statistics, you know, and thereby spoof what we had just seen from the quantum computer? Well, you know, in principle, yes, such a classical algorithm is possible, but, you know, we can give arguments, you know, that why we think that it would require tremendous resources to do. In particular, resources that scale at least like 2 to the 53 power. Now, Google, in its paper, estimated that with their supercomputer, with the fastest algorithm that they know, it would take about 10,000 years. You know, as we'll see, that was then considerably beat. Okay, but, you know, but the quantum computer is still winning by some margin. Okay, so let me maybe step back and discuss, you know, in general, you know, why are we talking about sampling tasks here? So, you know, when people talk about quantum computers, you know, what are the applications where a quantum computer is thought to give a speed up over classical computers? Well, you know, you may have heard of Shor's famous algorithm for factoring integers, right, and thereby breaking most of the cryptography that's currently used to secure the internet. So, you know, that's a tremendous speed up. That is, you know, and in some sense that would be like a gold standard for quantum supremacy, because you know, not only could you, you know, demonstrate that you would quickly factored this 10,000 digit number, let's say, but once you had done so, any skeptic who didn't believe you could just check your factorization for themselves, right? They could easily multiply the factors together. Okay, so the problem is that, well, you know, Shor's algorithm requires very, very precise control, and will surely require quantum error correction before you can do it. Okay, and that, in practice, that means that you're going to need, with the currently known error correcting codes, it means you'll need thousands of physical qubits for every logical qubit, and so then you're talking about millions of physical qubits. Okay, and there's the same problem with what's called Grover's search algorithm, which could get some, you know, more modest speed ups for combinatorial optimization problems and machine learning problems and things like that. Again, seems to require error correction before you'll see any speed up. Simulating quantum physics itself. By the way, I think that that's maybe the most important application of quantum computers, when and if we actually get them, get you know, scalable ones. That we have, you know, the best shot of you know, seeing some benefit even before we get to error correction. So, you know, let's say in the next decade or so. Okay, but you know, even that is going to be, you know, very hard to do if you want to outperform what all of the classical supercomputing people can do with you know, with quantum simulations. Okay, so so there's a you know, if our goal is just to demonstrate quantum supremacy, you know, in as clean and direct a way as possible, then there's a very different idea for how to do it. As far as I know, it was first proposed in a prescient paper in 2004 by Barbara Turhall and David DiVincenzo. And then the sort of modern push for this idea sort of started around a decade ago with papers by me and Alex Arkhipov and independently by Bremner, Jozsa, and Shepard. Okay, and this idea is to use sampling problems. So in other words, we're now going to look at problems that, unlike factoring, do not have a single right answer. Okay, we were just going to be asking for samples from some target probability distribution. Okay, now, of course, sampling problems also have a long history in computer science. They're right there in Knuth's, Art of Computer Programming. Okay, but what are the advantages? Well, these sampling tasks tend to be a lot closer to what a quantum computer would just naturally do, to sort of the natural abilities of the hardware. So you don't require a lot of expensive encoding that could be fatal to your quantum speedup. But in addition to that, if you don't care about usefulness, right? If you just want something that is hard for a classical computer, what Arkhipov and I and Bremner, Jozsa, and Shepard were able to do is to give very strong evidence that that these sampling tasks are going to be classically hard, maybe even stronger than the evidence that, let's say, factoring is hard for a classical computer, right? Which of course is just an assumption that nobody has yet proven. Okay, specifically, we were able to show that there are very simple quantum systems that can sample from probability distributions, such that if you had a fast classical algorithm to sample from exactly the same distribution, then what is called the polynomial hierarchy would collapse to its third level. Now, if you don't know what that means, you could take my word for it that it's bad. Okay, it is, you could say, it would be almost as shocking as if P were to equal NP. Not quite, but almost. Okay, and in the present state of theoretical computer science, this is close to the best that we can do to argue that a problem is hard. Now, in practice, that result is not directly relevant to the real experiment, because real experiments have a lot of noise in them. They don't sample from the true distribution, but only from some noisy approximation to it. So we have to worry about that. We also have to worry about, the fact that we never see what distribution is being sampled. All we can do is apply some statistical test to the output, and we then have to think about, well, would it be hard for a classical computer to do anything whatsoever that would spoof that test? Okay, so the disadvantage is, well, at least until very recently, we had no idea what any application of these sampling problems could be, except for refuting the skeptics. There's also a difficulty with the sampling problems, that even to check the results, to do statistics on the outputs, requires an exponentially long classical computation. Okay, so there's an irony here that we can do these experiments with, let's say, about 50 qubits, because 2 to the 50 power is just within where you're able to check the answer with the largest supercomputers that now exist. Okay, and you see that the quantum computer did the thing a lot faster, but you also see that the classical supercomputer did it also, and therefore checked the answer. You wouldn't want to do these kinds of experiments with 100 qubits, because even if you did it, even if it worked, we would have no way to simulate it classically and thereby verify that what you had done was correct. Okay, so at that point, you really will want to switch to, for example, simulating quantum physics, or simulating quantum chemistry, or one of these other applications where you could check the answer, either mathematically or by reference to a physics or chemistry experiment. Okay, so more specifically, what Google did is something that we call the random circuit proposal. And this actually emerged from an email exchange that I started with the Google team and with a bunch of quantum computing academics about 4 years ago, and we knew that Google was wanted to pursue quantum supremacy, and the question was, what should they do with, say, a 50-qubit device where they can verify the answer, and we're as confident as we can be that it will be hard to simulate it classically. Okay, so what we converged on was a very simple idea, which is that you challenge the quantum computer by sending it a randomly generated quantum circuit, call it C, on n qubits. So this is really just like some random sequence of interactions. They're arranged in staggered layers, like you see in this picture. So each qubit can talk to its neighbors, and if we can do a bunch of different operations in parallel, and if we stagger the horizontal and vertical ones in a way like this, we can get it so that after only a few layers, every qubit can send a signal to every other qubit. Okay, and then we ask our quantum computer to quickly send back a bunch of independent samples from the probability distribution that would be obtained sort of by the ideal version of this quantum circuit. That is, by applying this circuit to, let's say, the all-zero initial state, and then just measuring each qubit to see whether it's a 0 or a 1. Okay, each time we do that, it gives us some n-bit string. In this case, n is equal to 53. Okay, so you could call each of the strings S1, S2, and so forth. These are each supposed to be independent samples from D sub C, the output distribution that corresponds to our specific quantum circuit C. Okay, and then the next step is that we take these samples and then, using brute force with our classical supercomputer, we do a statistical test to see, are these samples consistent with having been sampled from this D sub C, from this quantum computer. And we add up the probabilities. For each string S sub I, we calculate its what would be the ideal probability of seeing that string. That's what this term here is, and then we add up all k of those. Okay, and that gives us just some number. Now, what value should we expect for that number? Well, if we had just chosen these samples S sub I uniformly at random, like with no relation to our circuit, well, each probability is 2 to the minus n on average, right? Because there's 2 to the n possible strings. So if I just add up a bunch of random ones, then I'm going to get on average about k over 2 to the n. Okay, but what I'm hoping for is to see a larger value than that. Okay, I'm hoping to see a larger value of this sum, because the strings that have the strings that are predicted to be more likely, that are supposed to have higher probabilities, well, I should be more likely to observe those, right? So how much more? Well, this is a calculation that you have to do, but it turns out that with a random quantum circuit, if you could really just sample from that perfect distribution D sub C, if there was no noise in your quantum computer, then the value of this sum that you would expect to see is about 2 times k over 2 to the n. Okay, so it's about twice the trivial value. Okay, and so now what we'll, in the real experiment, there will be lots of noise, but what we'll be looking for is some value of b in this expression here, which is detectably larger than 1. Okay, thereby showing that we were not just picking the strings at random. So, we're actually observing a correlation with the hard distribution that we wanted. This is a benchmark that Google called the linear cross entropy benchmark. It's a confusing name because this is not an entropy at all, but okay, it's just a sum of probabilities. Now, John Martinez, who was the leader of the experimental effort at Google, he likes to describe what's going on in terms of speckle. Okay, so I took a laser pointer and I sent the light through some ground glass and looked at where it ended up, I would see a speckle pattern that looks kind of like this. There are some light spots where there is sort of constructive interference between all the different paths that a photon could take to reach that spot. And there are also darker spots where there is destructive interference, where the different paths that the photon could take have sort of canceled each other out. Okay, now, if I could just send through even only a few photons, I could still check for consistency with this speckle pattern by doing statistics to ask, are the, look at the places where the photons landed, are they preferentially concentrated on the light spots of this diagram, the places where there was supposed to be more constructive interference? Okay, so in effect, we are just looking for a speckle pattern like this, but not just on a screen, but on a space of 2 to the 53 power possible outputs. Okay, on a set of 9 quadrillion possible outputs, and the intuition, however, is once again that if we look at each output, the amplitude of every possible output string is a sum of a whole bunch of complex numbers. Okay, the amplitudes of all the different paths that the computer could have taken to get to that output string. Okay, and for some of the output, for some possible output strings, there will have been a little bit more destructive interference. The different contributions will have canceled a little bit more perfectly. Okay, for others, there will be a little bit more constructive interference. Right, the cancellation will not have been as perfect. Okay, and so there will be little fluctuations in probabilities. All of the strings are exponentially unlikely, right? So even if you do the experiment perfectly, you never expect to see the same output more than once, right? Every string has a probability on the order of 2 to the minus 53. Okay, it's just that some of the output strings have a probability that is twice that much, or 3 times that much, or only half that much, and so on. And that is the that's the signal that you're looking for. Okay, if you want to know more precisely, the amplitudes just look like IID, independent complex Gaussian random variables, and the squared absolute value of a complex Gaussian turns out to just be an exponentially distributed random variable. Okay, so the probabilities act like exponentially distributed numbers. Okay, so that was Google's quantum supremacy claim. Now, some of you may have seen that even before Google's official paper came out, IBM, which is Google's actually main competitor right now in superconducting quantum computing, published a rebuttal. Okay, now IBM's initial rebuttal to Google was that they reject the entire concept of quantum supremacy because they only care about solving commercial real-world problems. I personally thought that was an incredibly weak response. But then maybe realizing that a few weeks later they came out with a much better response. Which is that, well, we don't think that Google achieved quantum supremacy anyway. And their argument was as follows, that if you take the largest supercomputer that currently exists on Earth, and that is Summit, which IBM knows about because they installed it just about a year ago at Oak Ridge National Labs. So this machine, well, it fills 2 basketball courts. It's got maybe 100,000 cores. And more important for our purposes, it has 250 petabytes of hard disk space. Okay, and they said that they estimate that by using Summit, they could just explicitly store the entire list of 2 to the 53 amplitudes in hard disk. And in that way, they could simulate Google's chip in a mere 2.5 days. Okay, so so you may notice the quantum computer is still faster. It was about 3 minutes, but 2.5 days. Well, that's a lot better than the 10,000 years that Google had said. And Google screwed up. They forgot to sort of think about what you could do by just writing everything to hard disk. They were thinking about doing everything in RAM, where you have to be much more memory efficient, but then that gives you a trade-off in time. Okay, so I'm glad that IBM pointed this out. That you could do this very, very naive thing, and that there are now on Earth supercomputers that are just barely large enough to do that have just enough hard disk. I also feel like if this is the strongest possible response, well then, the analogy that I use is that it's almost like the Kasparov versus Deep Blue chess match from the 90s, except with the enormous irony that IBM is now playing the role of Kasparov instead of the role of Deep Blue. That is, they're saying with heroic effort, you could use the largest supercomputer that is now on Earth to not quite, but maybe almost match the quantum computer, on this sampling problem. Okay, but now if Google had used, let's say, 55 qubits instead of 53, then already the list of amplitudes would not fit on the hard disk of this device. Okay, basically you need, if I have n qubits, you need 2 to the n floating point numbers, right? And so 2 to the 55 floating points, or 2 to the 60, that's already more than would fit in 250 petabytes. So then you start needing, even bigger and bigger supercomputers. And, so it seems clear that we're at some kind of crossover point where, at least for these very contrived or specialized quantum computers, the quantum computers are now on a trajectory where presumably from now on they will win, right? Yes, supercomputers will get better, but the experimentalists will be able to add qubits to their devices, and the classical resources scale exponentially with the qubits. Okay, so the sort of theoretical question was sort of, is there a barrier? If there's really some much faster way to simulate these random circuits on n qubits, let's say using time that was only polynomial in n, then that's the kind of thing that really would refute Google's claim of quantum supremacy. Okay, so it's crucial that IBM is not claiming to have sort of breached this 2 to the n barrier, right? They're still at the end just doing a brute force simulation on just a big enough computer. By the way, I should add that IBM did not actually do the simulation because it's not so easy to get 2.5 days of time on Summit. It's being used for, I don't know, probably nuclear weapons or, all kinds of stuff. They can't just commandeer it. Okay, but I think the more fundamental question is, could there be a classical way to spoof these sorts of experiments that did not have 2 to the n scaling? So, did not require these sort of monstrous resources. Well, so we know something about the theoretical trade-offs there, that, as you can trade off time for memory in these simulations, but all the simulations we know, use time that grows at least like 2 to the n power, like 2 to the number of qubits. Okay, and so I and others have done theoretical analyses, over the last decade that have where we've given some support for the conclusion that it is unlikely that there is a fast classical algorithm to spoof these sorts of experiments, in the sense that if there was one, if you had a fast classical algorithm, even just for spoofing, let's say, this linear cross entropy benchmark, then that would mean that you would also have a fast classical algorithm to just take an arbitrary random quantum circuit and estimate a specific amplitude, even a little bit better than like a trivial, guess would have been able to estimate it. And that's something that we have no idea how to do. Okay, so at least, there's nothing specific about this linear cross entropy benchmark that Google is using that is going to make that benchmark especially easy to spoof. Okay, so now the last thing, to mention is, well, the obvious objection to these quantum supremacy experiments from the beginning has been, well, even if they work, quote unquote, they're just solving a useless problem, right? In fact, they're just producing some string of bits that looks mostly random. You have to do this heroic supercomputer computation, even just to see that there are any biases away from pure randomness, right? And which is the signature of the quantum behavior. But just producing a bunch of mostly random bits, that seems pretty useless. Okay, the new idea that I had a couple of years ago is that, well, it's not necessarily completely useless. Generating random bits can be useful, particularly if you need to prove to a skeptic that you really did generate these bits randomly. Okay, and so the problem of certified randomness is actually really, really important in cryptography. A good example would be proof of stake cryptocurrencies. Okay, so these are cryptocurrencies like the next generation Ethereum that try to get the advantages of Bitcoin, but without using 1% of the world's electricity, on supercomputers that just sort of uselessly invert a hash function. And, so they're environmentally friendlier. The problem is that these proof of stake cryptocurrencies require a huge source of random bits, basically to run a lottery to decide who gets to add the next block to the blockchain. And, everyone has to trust that these bits really are random, okay? That they were not secretly biased. So how do you get over the internet? How do you get certifiably random bits, right? You can't just use your standard hardware random number generator. Why not? Because how would anyone know that you had not just swapped it out for some pseudo-random numbers that you secretly knew how to predict? Okay, this is where quantum supremacy experiments could potentially come in. Okay, so the key new insight that I had a couple years ago is that if a quantum computer passes that benchmark, that Google's linear cross entropy benchmark for quantum supremacy, then as a byproduct of that, it's proved more than just its quantum behavior, which or quantum computing speed up, which was the original point. Rather, even a quantum computer should have only been able to quickly generate samples that pass this linear cross entropy benchmark by generating them randomly, okay, in a way that has a lot of true entropy. Even a quantum computer should not have been able to quickly do it in a secretly deterministic manner. And one can justify that using further complexity theory assumptions. I don't know if this will be useful in practice, but we have licensed the intellectual property to Google now, and Google is, along with NIST, National Institute of Standards and Technology in the US, is currently working on the first demonstration of my certified randomness protocol. If it works, it could be, conceivably the first application of quantum computers for some definition of application. Okay, so there are lots of exciting places to go next. Can we get quantum supremacy with near-term devices, meaning like without error correction, but in such a way where we can actually easily verify the results using a classical computer, for example, in some cryptographic manner? Okay, I think that's risen to be maybe the most fundamental theoretical open problem right now, right? We don't want to be spending this heroic effort with a supercomputer just to verify what the quantum computer has done. Okay, and eventually Shor's algorithm, would be an answer to that. But we want to do it in the near term without needing error correction. Okay, and using something like these random circuit sampling experiments. Can we replicate Google's result in other hardware platforms with better fidelity and so forth? Can we try to refute Google's claim of quantum supremacy by designing better classical algorithms for simulating random quantum circuits? I think there has not been enough research on that fundamental question. And in the other direction, can we get better theoretical evidence for the hardness of simulating random quantum circuits? And then finally, there are many open problems, about making my certified randomness scheme more practical, such as can we get more and more certified random bits by just running with the same circuit over and over, which, if true, would enormously improve the bit rate. All right, so let me conclude. Google has apparently achieved quantum computational supremacy using random circuit sampling on 53 qubits, building on a lot of allegedly useless complexity theory that colleagues and I did over the past decade. Even if true, this leaves the enormous challenges of true scalability, requiring error correction and fault tolerance. But I think that it's already enough to refute the people who said that quantum computing speedups are impossible in our world. It was thought obvious for years that quantum supremacy experiments based on sampling had no applications. My certified randomness scheme might change that, although many challenges remain in making it secure and practical. Okay, so thank you for listening. I apologize for going over time, but if people are still here, then I'm happy to take questions.
Thank you. Please type your questions in the public chat.
In the public chat. So where do I find that?
That's for the attendees.
Oh, can you ask them?
Yes.
Sorry.
Yes, Krzysztof.
Sorry, I don't actually see the public chat. That's the problem. Yeah. Hi.
Thank you very much for your excellent talk.
Thank you.
Interestingly, I'm a theoretical physicist, and it's always amazes me how well you can explain quantum physics, which indeed takes years and years of study to get through all the nitty-gritty of stuff, and you do it on one slide.
I tried.
That's impressive, and actually it's all accurate. So that's great. And I have a question. In the meantime, when we ask for the question, I have a question. A couple of things. First one is about Summit. I don't think they do a lot of classified work because they belong to Office of Science at DOE.
Oh, but okay, probably not nuclear weapons then.
Well, that's what they do. A lot of interesting stuff. Now, if there was another implementation of numbers like posits from John Gustafson, where you can represent floating point. It's not floating point really. In, let's say, 16 bits, that is about 4 times less space in your storage, but that will give you about 3 more points in sort of N255 perhaps.
Yeah, exactly. A factor of 4 will give you 2 more qubits.
Yes. So not much advantage. Right. Another thing is, could you comment on complexity in parallel time? Because very often, one of the things that always puzzles me is molecular dynamics, where you have deterministic evolution of some time-evolving system with long-range interactions, and that kills you. So how would quantum computing help in parallelism in time?
Parallelism in time? Well, so I'm not sure that I fully understood the question, but I mean, typically, if you're trying to simulate a dynamical system, even with a quantum computer, you still have to, do it step by step, typically, right? And so this is one reason why we do not expect large quantum speedups for simulating classical dynamical systems, right? Only modest ones here and there, right? Where you can really expect a huge quantum speed up is for simulating quantum systems, where you can map the quantum states that you're trying to simulate onto the states of your quantum computer, right? But even the quantum computer, it's not going to be taking a sort of a magic shortcut through through the time of your dynamical system, right? You're still going to be just, let's say, if it's a continuous time system, you're going to be dividing it up into small slices and then just simulating the dynamics of each slice.
Okay. So do we have questions from the audience? Krzysztof.
Yes, we have two questions.
Could you read them?
The first one is from Mr. Piotrowski. Do you think there could be an efficient classical algorithm spoofing the verification without generating the right distribution?
So that's an excellent question. That was exactly what the entire point of our recent results was to try to address. Okay, so I mentioned briefly in the talk this paper that I had with Li Chen a few years ago, and a more recent paper with an undergrad at UT Austin named Sam Gunn. Okay, and the theorem that we proved in those papers, here's what it says. Basically, it says that if you had a fast classical algorithm to spoof the test that Google did, then that would imply that could take a random quantum circuit and that could take a specific amplitude, such as the final amplitude of the all zero state, and it could estimate it a little bit better than chance. Okay, and by a little bit better, I mean, the advantage that you get over chance is exponentially small, so it's tiny, okay, but it's still way, way better than what we would know how to get with any, efficient classical algorithm that currently exists, okay? And so if you think that, there is basically, no insight that you get into a random quantum circuit, without doing brute force, then spoofing, the benchmark that Google applied is going to be a hard problem. We're able to prove that conditional statement. Okay, now, so in other words, what this is telling us is the thing to focus on is not the benchmark, right? Despite what one may have thought, the thing to focus on is just what is the general difficulty of simulating random quantum circuits, and especially simulating random quantum circuits in the presence of noise. Right now, I should tell you that there have been some recent papers that have shown, like very recent, like the last few months, that have shown that if you have a random quantum circuit that is also noisy and is small depth, like it only has a few layers of gates, then there actually are much faster classical simulations that are possible. Okay, the hope is that, I mean, first of all, the depth that Google can do, I didn't mention this in the talk, they can do a depth of about 20 layers of gates, and that's already sort of large enough to, evade these theorems that seem to be talking mainly about depth 3 or 4. Okay, so, so we hope that we're evading that, but, there could just be some general insights into random quantum circuits or noisy random quantum circuits that no one has had yet. And that would be the kind of thing that, if true, could kill these quantum supremacy experiments.
Thank you. We have another question from Mr. Brahma. You have not highlighted anything about Intel's leadership in quantum computing. Is there some area that they're even close to Google or IBM in that?
The honest answer is that I don't know. I just haven't heard as much from them about. I've heard that that they're building superconducting qubit devices, and I think they're I don't think that they're publicly available. I don't know what the latest is with them, to be honest.
Okay, thank you. We have another question from Andres. What about the power consumption? Google's algorithm needed much less energy than the classical simulation. Is it fair to compare a supercomputer with millions of CPUs against a single QPU? Should quantum supremacy include also power consumption criteria?
Oh, sure. You could, I think it's totally fair to look at power consumption if you would like to. As I said, by that criterion, Google's Sycamore processor is winning, over, let's say, the Summit supercomputer, right? A dilution refrigerator is, somewhat power hungry, right? It is, certainly it uses a lot more power than my laptop does, but it also uses enormously less power than Summit does, right? And so, so the point is that, Summit has 100,000 cores, and, and that, huge number of cores is the only way that we know how to get even within striking distance of the quantum computer's performance for the sampling task, right? That's the only way you're going to do it in 2.5 days. But if you're going to allow that massive parallelism, in order to be competitive on time, as I think you ought to be, well, then it seems fair to also, look at the power consumption that you're using in order to do that.
Thank you. We have another question from Maciej.
Okay.
As I understood, in Google's experiment, classical computer was used for verification. What is the future of hybrid quantum classical computers and algorithm designs for those?
Okay, so you hear this term hybrid quantum classical algorithms a lot. I have to confess that I don't like it. And the reason I don't like it is that every quantum algorithm is a hybrid quantum classical algorithm, right? So in other words, anytime you're using a quantum computer for anything, right, you will, it only makes sense to use the quantum computer for those pieces where it will actually give you a speed up, right? And, all of the sort of control flow, anything connected with the user interface, right, any of that stuff, you might as well just do on your classical computer, because why not? Because you can. Right. And so the way to think about a quantum computer is it's an accelerator, right? It's like a coprocessor, maybe slightly analogous to, a graphics card or something, right? It is a coprocessor for accelerating, a few very special things, where you get a quantum speed up. But, even when quantum computers are used in practice, for some special tasks, as we hope that they will be, I feel like a lot of the application stack is going to be happening on classical computers, right? And so sort of every real application of quantum computers is going to be hybrid in that way. And you could say that the quantum supremacy experiment also was, in the sense that generating the random circuit, all kinds of stuff to control the circuit. That was all done on classical computers that are sending signals into the dilution refrigerator and then getting signals back out from it.
Thank you. We have another question from Jakub. From the perspective of efficient simulation of quantum computations, which conditions, computational power, etc., would you consider rationally imposed on a referee who should distinguish between simulation and quantum circuit itself? Google's and IBM's case seems to raise such an issue.
Okay, so I'm not sure if I understood the question. I mean, if you're a referee of a paper, then how do you tell if it's a real quantum computer or not? You apply, there are all the usual standards of refereeing, right? I mean, long before quantum supremacy, I think, one published papers saying, we use the quantum computer to do this or to do that. And, there's a certain degree of, believing, or trusting that the experimentalists, did not engage in fraud, right? That they did the experiment that they said they did. They got the results that they've reported, right? But of course, what we ultimately want is quantum computers that will sort of outperform classical ones, where where then it won't be based on trust anymore. It will be based on you submit a challenge and you get back an answer, and then you can just check for yourself that answer is correct and that you got it in a faster time than you knew how to get it otherwise. Right now, you could say that we are not yet at, we're not quite at that point. Okay, in Google's paper, they actually generated the challenge circuits themselves. Okay, and they also verified the results themselves. Actually, I should have mentioned this, but with their hardest circuits, they're 53 qubits and depth 20. It was too hard even for them to verify the results. They did not have access to full access to the power of Summit. We're not thinking about writing everything to hard disk. One of the great ironies, by the way, is that Google could now tell IBM, well, gosh, this is great that you have this way to simulate our chip. Now you go use that to directly verify our hardest circuits, right? Google had verified slightly easier circuits than those using supercomputer, using I think 1 million cores running for a month or something like that. Okay, but when they wrote their paper, yeah, there is some amount of trust in Google that they did, that first of all, that they generated the challenge circuits in an honest way, without somehow secretly making them easy. I'm not sure even how they would do that, even if that were their goal. But okay, we're trusting that they didn't secretly make the circuits easier, and then we're trusting that they did the verification correctly. Now that last part can be addressed. Google has put all of its raw data up on GitHub. Okay, so all the challenge circuits and all the data is available for download, and so anyone who wants to do an independent verification can start doing that right now. And if any listeners to this talk want to go and do that, that would I do think that there should be independent confirmation of their of the classical side of the verification of what they did. But as for generating the challenge circuits, I think that will come. What we would really like is for like an independent skeptic to be generating the challenge circuit, sending it to Google, and then seeing that it gets back an answer after only a few seconds. Okay, and I think that will come in a few years after or less. After the world, starts up again after the coronavirus, I don't think for the next few months there's not going to be much of any experimental quantum computing that happens. But once things start up again, so if you remember my randomness protocol from the end of the talk, this is exactly what my randomness protocol would require for an independent skeptic to generate the challenge circuit. Send it, let's say, over the internet to the quantum computing server, let's say to Google, and then get back the output samples, from the quantum computer within a very short time. And it could then verify those outputs at its own leisure. Okay, so that kind of setup, I think, that would be like an even, a more airtight demo of quantum supremacy. And I think that, the technology for that already exists, and hopefully that will be done soon.
We have 2 more very interesting questions, so maybe we'll sort of pose those questions.
Sure.
One is again from Jan Piotrowski. Are there problems other than sampling suitable for quantum supremacy on noisy quantum computers?
That is that's a superb question. And I would say that is a major focus of quantum algorithms research right now, right? Because we know that we're going to have these noisy devices with 50 or 100 or 200 qubits over the course of the next decade. and we don't really know what they're good for. Okay, we can do this demonstration of quantum supremacy, which Google just did, and that's great. We could improve, make that demonstration more airtight. But of course, it would be even better if we could do something useful. I think that the best shot, as I mentioned in the talk, I think that the best shot that we have for doing something useful with these noisy near-term devices is going to be to do some kind of quantum simulation, probably of some materials, of some condensed matter system. Although if we're really lucky, then maybe even of chemistry, of some chemical reaction. And that would tell the scientists in the relevant area, the material scientists, the condensed matter physicists, the chemists, that would tell them something interesting about their system that they didn't already know. I think that would be a tremendously exciting next milestone. And it is possible that we could achieve that using noisy devices. I mean, in some sense, we already have special purpose quantum simulators that already do things that are like that, right? Misha Lukin's group is already doing things of that flavor. Okay, but they're doing it with like you just build your quantum simulator just for solving one problem. And we would actually like to see a general purpose programmable quantum computer, that could do any, problem of that kind. And we would like to see it actually used to get some useful results for some quantum simulation problems. So that's what I'm hopeful that we'll start to see, over the next decade or so. As I said, that's probably the best shot. There's a lot of talk about other applications for near-term quantum computers, like, for example, for optimization and machine learning. It is crucial for everyone to understand that those applications are very, very speculative, okay? Meaning that even if you have a perfect quantum computer, we still don't know what kind of speed they're going to give you, right? So that's very important to realize.
Okay, we have the last question from Raoul Klocker.
Okay. Sure.
Can quantum computers be networked comparable to local wide area and internet networking of traditional digital computers?
So absolutely, they could be. So there's even some discussion about building a quantum internet. That would simply be an internet where you could send qubits over long distances. Now, unfortunately, I would not say that we have a real killer application for a quantum internet. I mean, the main application that we know of for being able to send qubits over a large distance is quantum cryptography, right? Quantum key distribution, which is already practical today over shorter distances. But there's been a very, very tiny market for it. And, the main reason is obvious, that it's sort of the problem that it solves is already well solved by conventional encryption, right? After quantum computers come along and they start breaking some of our conventional encryption, then ironically, that may create more market for quantum cryptography. Okay, but, right now, even then, there are, other forms of cryptography that seem to be quantum resistant that we could migrate to. And so it's not clear why you need to be able to send qubits over huge distances. But having said that, there are certainly huge problems in, let's say, networking together the different components of a quantum computer, or if you want to say it differently, just networking together multiple quantum computers, multiple cores, if you like. And if you look at the proposals for how are you really going to scale this up. How are you going to get either trapped ions or superconducting quantum computers that would have many millions of qubits rather than just a few hundred qubits? That would absolutely involve networking together a whole bunch of prefabricated components, and then having a little quantum intranet, so to speak, where you could actually send route the qubits within between the different components of this device. So there's lots and lots of engineering problems there, and lots of engineers who are thinking about that.
Thank you very much, Scott. That was great, and we really appreciate your time. And on behalf of everybody here in the audience. I'm sure there were more than 100 people from all over the place. We're very grateful for sharing your knowledge. And now, going back to the last question, if Raul, please, you can go to the Supercomputing Frontiers Europe website. Precisely a week ago, we had the pleasure of hosting Eden Figuera from Stony Brook University, and his entire lecture was on quantum Internet. That might add to you. And of course, we'll be putting on our website the lectures from that conference. Right now, I would like to announce the second in a series of our seminars. If I may ask Krzysztof to put this information right. In a week's time, we'll have a pleasure of hosting Professor Errol Gelenbe from Imperial College London, who is very well-renowned computer scientist working in the era of networks. There are famous G networks that he invented, and his areas of interest is in cybersecurity and self-healing networks, and the title of the next talk will be a Dynamic Self-Aware Approach to Cybersecurity. For those of you who came to our seminar solely because of the topic of quantum computing, please don't despair if cybersecurity is not your main interest. We will have new more talks on quantum computing. I've already received a confirmation from Arthur Eckert, Professor Arthur Eckert from Oxford and from National University of Singapore, who is very well-known researcher in the area of quantum algorithms. So that will happen in a few weeks' time. I don't have an exact date yet, but for those who are following quantum computing developments, there will be more in this series. Please check regularly our website with the titles of forthcoming talks. And as you might realize, it's a very new initiative, and we are just doing the sort of evolving as we do it. So I can only now announce next week's speaker, and that will be Professor Errol Gelenbe. And I can assure you that this will be a very, very interesting talk related to computer networks and also energy networks and also cloud computing and all similar things, how it all ties in together. So I welcome you to the following seminar, and thank you very much for coming to this one. And I'm sure that you've all enjoyed today's experience. Thank you very much.